Okay, so we continue with our theorem for composition, and here we say let f be continuous at a point x is equal to a, x is equal to a in the domain of f, and let G be continuous at a point f of a in its domain. And now we say that then the composite function G naught f is continuous the composite function G naught f is continuous at x is equal to a, and we can actually prove this. So to prove this, we start with what is given in the theorem, f continuous at a. So we can say that f continuous at x is equal to a implies that the limit as x tends to a of f of x is equal to f of a, and then g continuous at f of a. So we say g continuous at f of a implies that the limit as y tends to f of a of g of y is equal to g brackets f of a. That's basically what the two assumptions here mean. Now, we have to show that g naught f is continuous at x is equal to a. So I'll remove this and write up here. So I'll say so that now we show that limit as x tends to a of g naught f of x is equal to g naught f of a. That's basically what we have to show, and this will actually show that g naught f is continuous at x is equal to a. So limit as x tends to a of g naught f of x will be the same as the limit as x tends to a of g brackets f of x, where I have used the definition for composition to write it in that form. And we say that let y to be equal to f of x. So since f is continuous at x is equal to a, since f is continuous at x is equal to a, the variable y approaches f of a. The variable y approaches f of a as x approaches a. thus the limit as x tends to a of g naught f of x, which was the limit as x tends to a g brackets f of x, will actually be the same as the limit as y tends to f of a of g of y. That's basically what it will be, and we know that this is going to be g brackets f of a, and this is because since g is continuous, this is because since this here is since g is continuous at f of a. And we know that this is actually the same as g naught f of a. This is actually the same as g naught f of a. Therefore, it is clear from here that g naught f is continuous at x is equal to a. An example we can have here. An example here is that the function h of x, which is equal to the absolute value of x cos x sin x divided by x squared plus 13, is continuous at x is equal to at any point is continuous, since it is a composition of, let me say, g naught f of continuous functions f of x, which is equal to x cos x sin x divided by x squared plus 13, and g of x, which is equal to the absolute value of x. The question maybe for you guys, which you can, the question for you guys is that are you sure that f is continuous? I'll leave that to you guys, but here it is, we are just trying to make use of the previous theorem, which says that if you have two continuous functions, then their composition is also a continuous function. So you guys can look at this function and say, is this function really continuous everywhere? But I'll tell you that the function is continuous everywhere. Now, let us do some examples. Another example. State the interval intervals on which the function is continuous. And an example, for example, you can have a function of this sort: x divided by cos x And let us say maybe b is f of x, which is equal to x plus 2 divided by x squared minus x minus 2. And maybe I'll say c is f of x, which is equal to, for example, 1 minus x, for x is also equal to 2, and then x minus 1 for x greater than 2. Let us, for example, look at these examples, and we are to state the intervals on which the function is continuous. Now, when you look at the first function, we are going to say this function, by the way, is not continuous whenever the denominator here is 0. So if the denominator is 0, the function is not defined, because this will be x over 0, and therefore the value f at that point will not exist. So here the intervals, of course, are many, so you just have to remove all points at which cosine of x is equal to 0. And we know that, for example, cosine of x is equal to 0 at x is equal to, for example, plus or minus pi by 2, 3 pi by 2, 5 pi by 2, and so on. So along the real line, if you can remove all points at which the denominator here is 0, then the function, actually, this function will be continuous, because this is a continuous function, this is a continuous function, but you have to remove all points at which cosine of x is equal to 0. Remember, we said that the fraction of two continuous functions is continuous at all points where the denominator is not 0. So an example, for example, I can give you where this function is continuous. An example of an interval, I can say from minus pi by 2 to pi by 2. That is, for example, an example where this function is continuous. But there are also others. You can say, there is also a plus or minus. For example, you have 3 pi by 2 to 5 pi by 2. Pi by 2 to 3 pi by 2. 3 pi by 2, etc, etc. So we can just, okay, I'll use this pi by 2 to 3 pi by 2, and then 3 pi by 2 to 5 pi by 2, and so on. What about this function f of x? So if you can factorize this, for example, you can see that this is x plus 2 divided by, this is going to be x minus 2 into x plus 1. That is basically how it's going to be. And then if we can remove these points, this is a continuous function because this is a polynomial. This is also a continuous function because it's a line, or it's a polynomial. So this is a fraction of two continuous functions, and this will be continuous everywhere except where the denominator is 0. So the interval where this function is continuous is going to be the set R minus the points where this function is 0, which is 2 and negative 1. 2 and negative 1. So if you can remove these points, then the function will be continuous everywhere except at these 2 points. And now we have this one. This is a piecewise. So first of all, we are going to say what is f of 2. Here, by the way, this is a line. This is also a line. Or this is a polynomial. This is a polynomial of degree 1. So this function is continuous everywhere. This is also continuous everywhere. But now this is a piecewise defined function. So what we need to do is to just check at the point where the interval breaks. And this is at the point 2, because this is where the interval for the function is breaking. So we can say that f of 2 is actually going to be 1 minus 2 because it's in this interval, which is equal to negative 1. And now we just need to say what about the limit at 2. So we are going to say the limit as x tends to 2 minus of f of x is going to be the limit as you approach 2 from the left is going to be here, which is going to be 1 minus 2, which is going to be negative 1, whereas the limit whereas if you compute the limit as x tends to 2 plus of f of x, that means we are going to be in this interval and you're approaching 2 from the right. This is going to be 2 minus 1, which is equal to 1. And you can see that since the limit as x tends to 2 minus of f of x is not equal to the limit as x tends to 2 plus of f of x, then the limit as x tends to 2 of f of x does not exist. And because the limit does not exist, then the function is not continuous at the point 2. Because remember, the definition of continuity says that a function is continuous at a point if the limit as x tends to that point of the function is equal to the value of the function at the point. So if one of them is violated, for example here the limit does not exist, then automatically the function is not continuous at the point. Another example we can give, I can give another example. Another example we can give is that given I'll say that the given function has a removable, the given function has a removable discontinuity. A removable discontinuity at x is equal to a. And I told you before that any removable discontinuity, the function can always be redefined to remove the discontinuity, because it's usually just at a point, and by redefining the function, you can actually remove the discontinuity. At x is equal to a, determine how f of a, how to define f of a so that the function is continuous, at a. And here, for example, you can consider the function f of x is x squared minus 1 divided by x minus 1 at a is equal to 1. And let us see another example. Is, for example, f of x is x squared plus 1 for x less than 1, and then root of 3 plus x for x greater than 1. So only one. So here, how can we define f so that it is continuous at the given point? Now here, remember, we have f of x is this. By mere fact that at a is equal to 1, it is clear from here that f of 1 is not defined. Because when you put 1 here, this will be 1 minus 1 divided by 1 minus 1. So it's over 0. So the function is not defined at 1. But if we compute the limits as x tends to 1 of f of x is going to be the limit as x tends to 1 of x squared minus 1 out of x minus 1. And you guys know that this will be the same as the limit as x tends to 1 of x minus 1, x plus 1 divided by x minus 1. And this cancels with this. So this will be the limit as x tends to 1 of x plus 1. So this limit is going to be 2. So because the limit is 2, as you approach 1, whether you approach it from the left or from the right, but the function is not defined at 1. So if you want to redefine this function so that it is continuous at the point, so maybe I should have noted first is that f of x is not defined at x is equal to 1. Because when we do this, but we have already found that the limit is 2, so we can redefine f as follows. So you say that f of x is like this. It's going to be x squared minus 1 divided by x minus 1 for x not equal to 1. And then you say it is 2 for x equals to 1. So if you redefine it like this, let the function take up the value of the limit at the point, then this makes the function continuous at the given point. Now, the second one, this is x squared plus 1. So I remove this. The second one is x squared minus 1. So here, f of 1 is not given. So when you see here, this is for x less than 1 and then for x greater than 1. And you can see that if you take the limit as x tends to 1 from the left of f of x, this is going to be the limit as x tends to 1 of x squared plus 1, and this limit is going to be 2. What about if you approach x from the right? Now, the limit as x tends to 1 plus of f of x is going to be the limit as x tends to 1 of root of 3 plus x. And when you put 1, this is going to be root of 3 plus 1, which is going to be the square root of 4, which is 2. So we can see that the limit from the left and from the right is 2. And what does that imply? That implies that the limit as x tends to 1 of f of x is going to be equal to 2. So we can actually redefine this function and say therefore redefine f as follows. We can say that f of x, you can do this, say x squared plus 1 for x less than 1, give it a value 2 for x is equal to 1, and then 3 plus x for x greater than 1. So we can actually redefine it like this. And when you redefine it like this, then the function is going to be continuous at a given point. Another example I can do that we can do is let me do one more example, then give you some exercises to try out. Example, find the constant k that makes the function f of x, which is equal to k for x greater or equal to 1, and then 1 out of root kx squared plus 1, kx squared plus k, kx squared plus k for x less than 1, continuous at x is equal to 1. So find the value of k that makes this function continuous at x is equal to 1. So remember, we said that if continuous at x is equal to a, if the limit as x tends to a of f of x is equal to f of a. That is basically the definition for continuity. Now here, we can first of all say what is f of 1. In this function, what is f of 1? 1 lies in this interval, so f of 1 is actually going to be k. Now, what is the limit of f as you approach from the right, and what is the limit as you approach 1 from the left? So we can say the limit as x tends to 1 plus of f of x is equal to the limit as x tends to 1 of k, and this is going to be equal to k. What about if you approach the limit as x tends to 1 minus of f of x, as you approach 1 from the left? It's going to be the same as the limit as x tends to 1 of 1 out of the square root of kx squared plus k. Kx squared plus k. And what would this be? As x tends to 1, this is going to be 1 out of the square root of kx squared. X is 1, so this is going to be k plus k, which is 2k. Of course, k cannot be 0, because if k is 0, then you have 1 over 0, so that limit, no, does not exist. So you can see that this is the limit on the left, and this is the limit on the right. And remember that for the limit to exist, the left-hand limit and the right-hand limit have to be equal. So we saw that for the limit as x tends to 1 of f of x to exist, then lim as x tends to 1 minus of f of x should be equal to the limit as x tends to 1 plus of f of x. And what does this imply? This implies that k has to be equal to 1 out of root of 2k, which of course k cannot be 0, and that has to be made clear because this will not be defined, and therefore here you will have that k, or k, this is square root of k times k, so this is k times the square root of k is equal to 1 out of root of 2. Which implies therefore that k to the power, this is going to be 3 over 2, it's going to be 1 over root 2, therefore k is going to be 1 over root 2 to the power 2 divided by 3. This will be the value of k for which the limit exists, but remember, since f of 1 is also equal to k, then the function will be continuous if we give k that value. So you guys can try out these exercises. So some exercises you guys can try is one, state the intervals for which the function is continuous. For which the function is continuous. And part A is, for example, you have f of x squared plus x plus 1 divided by x cubed plus 2x squared minus 3x. Part B, for example, you can have f of x is equal to 1 out of 1 plus x to the power 2 over 3. C, for example, you have a g of x which is equal to x to the power 2 over 3 minus x to the power negative 2 over 3. And then D, for example, you can have an h of x which is equal to piecewise defined function, which is x squared for x less than 0, and then 3x for x greater or equal to 0. And then question 2. So this is 1. So question 2. Question 2 is we define f so that the function is continuous at a. X is equal to a. And part 1, for example, here you have f of x is going to be x squared minus 1 out of x minus 1 at a is equal to 1. 2, you have f of x cos squared x minus 1 divided by sin x at a is equal to 0. And part 3 is f of x is equal to x squared plus x minus 2 divided by x cubed minus x squared minus 6x at a is equal to negative 2. So you can redefine these functions so that they are continuous at the given points, at 1, at 0, and at minus 1. And then another question you guys can try question you guys can try is find the constant k that makes the function continuous at x is equal to a. Find the constant k that makes the function continuous at x is equal to a. And an example here is f of x, which is equal to x power k for x less or equal to 2, and 10 minus x for x greater than 2. And here we are talking about the point a is equal to 2. And then b is f of x, which is given by x minus k, x plus k, x plus k for x less or equal to 2, and then kx plus 5 for x greater than 2. And here we're talking about k is equal to 4. So you can try some of these. Maybe one more question which you can try. One more question which you can try, question 4, is use the fact that the limit as x tends to 0 of sine x over x to be equal to a, to evaluate the limit one is that the limit as x tends to 0 of sine 6x over x. 2, the limit as x tends to 0 of 2x divided by sine x. And 3, the limit as x tends to 0 of tan 2x over x. And then lastly, the limit as x tends to 0 of sine x divided by sine 3x. Try out some of these. Maybe 5 also is the limit as x goes to 0 of sine x divided by the sine of dx. And 6 is the limit as x goes to 0 of x cosec 3x. You guys can try out this, and then we shall continue from here tomorrow.